Hi everyone, thanks for watching this contribution. I am Eleonora Alei, postdoc at ETH Zurich, and I'm going to talk about my current project, the diagnostic potential of a mid-infrared space interferometer for studying Earth analogs. The interferometer we're talking about is LIFE, the Large Interferometer for Exoplanets. This is a proposed mission to study planets in direct imaging with a focus on terrestrial potentially habitable ones. To know more about this mission, I suggest you have a look at the other contributions about life at EPSC 2021. Our team worked on a retrieval framework that was used to characterize an Earth twin if it were observed by life. We simulated the data using petit reference, which is the same forward model used in the retrieval framework. And we give an estimate on the observed noise using LifeSim, the official noise simulator for life. We found that the minimal technical requirements necessary for life to characterize the atmosphere of a modern Earth twin were a resolution of 50, a signal-to-noise ratio of 10, and a wavelength range between 4 and 18.5 micron. We want now to depart from the modern Earth scenario and understand how life would characterize other atmospheres. In the context of habitability, it's particularly interesting to see how the various stages of the evolutions of the Earth's atmosphere would be characterized by such a mission. But from the technical point of view, we also want to remove the bias that's caused by using the same forward model to produce the simulated observations and to retrieve the results. So using spectra produced by other models would help us understand the performance of the retrieval framework and the potential systematics. And I'm going to jump directly to the answer to these questions. The current framework is capable of qualitatively distinguishing between the various stages of the Earth's evolution, and it performs fairly well when using data provided by other groups. Now, I will motivate these answers with a few more details. The atmosphere of the Earth has undergone substantial changes throughout its evolution, mainly due to the appearance of life on the surface of our planet. In this plot, you can qualitatively see how some of the main components of the atmosphere have evolved in time, starting from 4.5 billion years ago until today. You can also notice that some particular events have caused important increases in the oxygen abundance, such as the Great Oxygenation Event 2.4 billion years ago, and the Neoproterozoic Oxygenation Event 0.8 billion years ago. In this study, we consider 4 specific epochs: a prebiotic Earth at 3.9 billion years ago, an Earth at the Great Oxygenation Event, an Earth at the Neoproterozoic Oxygenation Event, and the modern Earth. We used both cloud-free and cloudy spectra produced by Ruckheimer and Kaltenegger in their 2018 paper. These were produced starting from temperature profiles and abundances profiles that were produced by a self-consistent climate photochemistry model, and we assumed the technical requirements for life defined in our previous study. So between epochs and cloud coverage, we have then 8 input spectra. We retrieve each of them using 2 different retrieval options. A simpler one, which excludes collision-induced absorption and thermal and surface scattering, and one that includes both processes. The latter is more complex and accurate, but it increases the computing time of the retrieval. Our setup presents some limitations, which are linked to the maximum number of parameters that our framework can retrieve for in a reasonable computing time. We therefore use a 4th-order polynomial approximation to the PT profile, and we assume altitude-independent abundances of the various species, while we know that the original abundances profile are altitude-dependent. We also consider a uniform surface reflectance when scattering is included in the model, and we retrieve both cloud-free and cloudy spectra, assuming no clouds in the retrieval. This allows us to understand what issues may arise when studying a complicated spectrum by using a simplifying assumption. And here are some preliminary results of this ongoing study. With respect to the abundances, we notice that the retrieval is able to detect the abundance of carbon dioxide, which varies a lot from epoch to epoch, ranging from 15% abundance in the prebiotic Earth until the modern 400 parts per million. The retrieval is not sensitive to N2, O2, CO, and N2O in any of the model scenarios. This comes to no surprise, since these species don't show evident signatures in the mid-infrared and get blended in the noise. This is also coherent with what previously found in the validation study. But when it comes to other species in the atmosphere, we notice that the retrieval performances change when changing the epoch. For ozone, we are able to detect abundances around 10 to the minus 7 about the current mean abundance of ozone. For lower abundances, we only get upper limits or non-detection. This allows us to rule out higher abundances of ozone in the prebiotic Earth and the great oxygenation event Earth. Similarly, we only detect methane when its abundance is larger than about 10 to the minus 4, which happens in the two oxygenation events. The water content remains more or less constant in the 4 epochs, but the retrieval in some cases struggles at detecting it, only retrieving upper limits. This may be a consequence of a few systematics that we want to identify as one of the goals of this study. Here, I'm showing you a comparison of the retrieved values for the planetary mass and radius, the ground pressure and the ground temperature for the cloud-free and cloudy models of the modern Earth, shown in blue and orange, with the two options with and without CIA and scattering represented as dots and squares respectively. I take the modern Earth as an example, but the other epochs show similar results. When it comes to comparing the retrieval options, we notice negligible differences. Any effect produced by CIA and scattering is very small at this wavelength range, resolution, and signal-to-noise ratio. We notice that the ground pressure is underestimated, which means that we retrieve thinner atmospheres. This is due to a compensation effect that the retrieval applies to reproduce the spectral signatures of the main absorbers, essentially water and carbon dioxide, which are themselves retrieved with uncertainties. In this case, we are limited by the resolution of the data. Validation runs performed at higher resolution eliminate this problem. The retrieval, which we recall is always cloud-free, produces consistent results for both cloud-free and cloudy spectra. The only difference is that cloudy models show a cooler ground temperature with respect to cloud-free models. This is a well-known effect of cloud-free retrievals, and while there may be negligible differences in the detected abundances, this effect may be relevant when discussing the habitability of a planet. It is therefore very important to add clouds in the retrieval framework, a project that has been started and it is discussed in another contribution to this conference. Last thing to discuss, systematics. In this plot, we compared the original spectrum at resolution 50 and SNR 10, the blue line and the gray shaded area, with the spectra produced by Petit Reference, which is the forward model used by the retrieval framework, using the input pressure temperature and abundances profile, including and excluding scattering, respectively in orange and green. As we can see, the spectra look different, despite using exactly the same input atmosphere. Possible causes to these differences could be the choice of different line lists or broadening coefficients, or differences in the models that produce the spectra in the first place, and in the way they treat relative transfer or the scattering. These systematics may justify the larger uncertainties on some of the abundances. So, to conclude, coming back to the questions we wanted to answer, our routine is capable of retrieving good results, even when using a more complicated simulated spectrum. There are a few limitations and systematics to pay attention to, but it's important to address and quantify these in order to have more robust results when the actual observed data will have to be retrieved. Most importantly, we learned that the current setup of life can distinguish between different atmospheres, especially when it comes to detecting prominent molecules that could act as tracers of the evolutionary state. Studies like this one also help us understand what would be the best resolution and signal-to-noise ratio to aim for in order to characterize planets different than the Earth. This is essential at this point in time to make an informed choice when it comes to defining the requirements for the life mission. Thank you for your attention and enjoy the rest of the conference.